So, unless I'm mistaken, this is the 25th Sanielevici lecture.
Right.
That's a great thing. So, the Sanielevici lecture is in memory of a former student of ours, Emil Sanielevici, who I did not know personally, but as far as I know, was well known for being extremely curious about all kinds of things. Very interested in research, very broadly interested. And so this lecture series was set up in his memory. And it is the 25th anniversary of that lecture series. And it's to commemorate that type of inquisitiveness and curiosity and engagement in research. And we have at least one former winner in our audience. I don't see Patrick. Melanie is a former Sanielevici Scholar winner. And nobody here is actually sure if this is true, but I'm just going to say it. This is the first lecture in which there's a physical demonstration object. So let's all pretend that that's true. And to kick it off, I'm going to introduce my colleague, Pranava Surukuchi, with whom our current Sanielevici winner is working, and you can introduce it.
Yeah, we can talk. Good afternoon, everyone. I'm very excited to introduce Kyle Mo. Kyle has been doing research in many areas within our department. So he's been working with Professor Woodwasey with the Rubin telescope. He's been working with Professor Hong on Atlas experiment on some of the trigger monitoring work. And since last summer, he's also been working with this development of this detector. While this looks like a very small detector, it essentially embodies everything what a particle experiment contains. And Kyle has been crucial for all aspects of this detector development, all the way from characterizing the components to building it, assembling it, and taking data and analyzing it. So without any further ado, I'll let him talk about the detector.
So, hi everyone, I'm Kyle. I first want to sort of thank everyone who's present tonight on Zoom. It means quite a lot to me. And yeah, you might have noticed that there's a blinking object right to my left. And for those in the back, or you can't quite see it, that's the same object. And I won't keep you in suspense. And in fact, you might have read the title and put two and two together. But what you're seeing here are these sort of blue LED tracks, which represent cosmic rays going through this sort of black box structure right below. Now, sort of the focus of today's talk is all going to be about this guy right here, which we call mini CoRTEx. And sort of the purpose is sort of twofold. One, it's sort of an educational detector, so you're going to get the basics feel that I do every time when I talk about this project, right? What are cosmic rays? Why are they important? The basics of how this device works, all that sort. But my sort of secondary purpose today is sort of beyond that, as I know there's a lot of students in here. And I sort of want to expose all of y'all to sort of characterization, instrumentation, and sort of design efforts that are involved with detectors in the first place. As I think it's very, especially as students, to look at these larger experiments, whether it's Atlas and the particle detectors multiple stories high, or you look at these detectors in like Antarctica or in the mountains, it's very intimidating to look at the actual things that take the data. So hopefully at the end of the talk, you'll know how we built this guy, mini CoRTEx, and, you know, perhaps apply it to your own physics and research. So to do that, let me sort of lay out the basic questions that I'll follow. The overall one being, how did we get here? But of course, I'll talk about what we're detecting. Already spoiled it. It's cosmic rays. But what exactly are they? I'll go into that. Why are they important? I'll then sort of transition into, okay, at this point, we know what cosmic rays are. So how do we theoretically detect them? What are the physics principles we can leverage? And then we'll sort of turn on our engineering hard caps and turn to how do we actually build it? What are the challenges involved? What are the characterization efforts needed? And so on. And then I'll finally close out what's the sort of overall broad picture of our group and our sort of future plans. Not to spoil anything, but this is called mini CoRTEx, which the word mini there somewhat implies that there's going to be a big CoRTEx. So we'll talk about that. So yeah, let's get started with that first question to just sort of get everyone on the same page. What are we detecting? We're detecting cosmic rays. And the best way I can explain it for this talk is that constantly Earth's atmosphere is being bombarded by protons and helium nuclei. And when they hit the atmosphere, they interact with all the molecules in it, the oxygen, the nitrogen. And as a result, there's sort of a showering of secondary particles. The most common charged particle that actually reaches Earth's surface, as you can kind of see in this diagram, is called the muon. And the best way to think about the muon for this talk is that it's just a heavier electron. It's about 200 times heavier. Like an electron, it has charge, so a muon can either be positive or negative. And there's some other similarities, like its electron has an integer spin, which is important quantum mechanically. So when I say this is a cosmic ray detector, you might also see me refer to it as a muon detector. We're detecting cosmic ray muons. So muon, cosmic ray, have those sort of interchangeably as I go through this talk. And to give you a sense of how often they occur without just looking at these tracks, if you hold out your hand, about 1 or 2 go through it every second. So they're quite ubiquitous. It's a good source. They're relatively energetic, about 3 or 4 GeV. For reference, the mass is around 125 MeV. So that sort of is the sort of boring definitional stuff. But that doesn't necessarily answer the question of like why cosmic rays, why are they important, why are we choosing to detect them to begin with. And it turns out that the sort of story of the cosmic ray is pretty much the story of early particle physics. So to sort of express that importance, we're going to take a quick detour into a little bit of a history lesson. You might have heard of this guy named Coulomb. He had this device called the electroscope. And the electroscope, you can think of as just, for now, something that can like hold charge and discharge. And Coulomb noticed that when he exposed the electroscope to air, it discharged. And that's weird, because you know that air is a good insulator, right? There's nothing innate about the air necessarily, besides maybe some imperfections, that would cause this phenomenon. So this sort of became the open question that would lead to the discovery of the cosmic ray. And it took quite a bit of time. The next bullet point I have here is when the fantastic Nobel Prize winning physicist Marie Curie won her Nobel Prize for sort of discovery of radioactivity and really sparked that study. And people noticed that radioactive particles would discharge the electroscope. Okay, so we'll sort of put these two ideas together. We know that when you expose the electroscope to air, it discharges. We know that radioactive particles, when you expose it to the electroscope, discharges. Therefore, there must be some radioactivity in the air. So that's a good theory. But there's sort of a huge part of that theory that I'm missing. Like, where are they coming from? Right? And the sort of 2 predominant thoughts at the time was that either came from the soil beneath our feet, the earth, or it came from the sky. So this sort of kickstarted a bunch of experiments in the early 1900s. I'll highlight 2 of them. This man named Theodore Wolff, he took the electroscope to the top of the Eiffel Tower. Why? Because theoretically there are radioactive particles showering on us. As you raise your altitude, there's less air above you to shield from these particles. All right. So theoretically, as you increase altitude, you should see more radioactivity. So he took it up. Turns out it's inconclusive evidence, which makes sense, knowing what we now know today. Kind of need a drastic difference. So that's one. Then another one, I don't quite know how to pronounce this, but Italian guy, Pacini, he took this boat right here, and he did the reverse. He put the electroscope 3 meters deep underwater. And again, at this point, it's a little bit more conclusive, but it wasn't really until this guy came around named Victor Hess. He took the most modern aviation technology at the time, a hot air balloon, and the electroscope, and he took it up, and he saw the results that we know today, which is there's an increased sort of radioactive presence as you increase with altitude. Right. And he was the one who actually sort of started this term cosmic, that there are these cosmic particles that are showering on us. So this is great. we now sort of know the answer to Coulomb's question all those years ago. But coincidentally, in the early 1900s, there was another major breakthrough in sort of instrumentation and particle detection, and that's the invention of the cloud chamber. And I'll show pictures later, but a cloud chamber actually allows you to visualize a particle track inside the actual chamber as it travels, which obviously you can use for study. And then, let's see, 1929, Dmitri was the first one to actually use a cloud chamber to actually visualize these cosmic ray tracks, right? You're not just seeing the results of cosmic rays, but you're actually seeing the particles themselves. And to sort of express these two innovations at the time, the cosmic ray discovery and the cloud chamber, I'll go through a brief story. And I like this quote because I think it expresses the importance. At the time, there weren't particle accelerators, so particle beams at CERN, right? So if you wanted to look at high energy particles, you would look at the cosmic ray. It was the highest energy thing you had, and it's free. You have a cloud chamber, you can make one. So to sort of show this, here's a very famous picture of Carl Anderson next to a cloud chamber. You can't quite see it because it's wrapped in coils, and you do that to generate a magnetic field, so then you can study the particle further. And you're like, okay, that's cool. He has a cloud chamber that's big. What did he do? Well, for one, he discovered what we now know as the positron, right? So you can actually see the track of this particle right there. And if you're like, what's better than discovering one particle? It's discovering another one. Now, this one wasn't instantly called a muon due to other historical details. But once again, these are pictures within the cloud chamber, which allow you to actually visualize the particle track. And this is what I mean by early particle physics. The history of it was often defined by the history of the cosmic ray. Now, obviously, this would somewhat fade out because we did invent particle accelerators, cyclotrons, particle beams, right? But that doesn't necessarily mean that the purpose of cosmic rays and cloud chambers went away. In fact, I'm going to argue that it sort of transitioned. Transitioned where? To the classroom. So you can see here all the way on the left are students making their own cloud chamber. This is CERN teaching you how to do it, and there's a museum exhibit of one. And this makes sense, right? You're actually seeing a particle that you can't see with your visible eyes. It's oftentimes the student's first opportunity to see this phenomenon, right? And in fact, I think we have one here at Pitt, which we can bring out. So this is sort of the modern day cases, right? You get it. Introduction to particle physics, and also introduction to this very important cosmic ray, which has been important historically. But this comes with a few issues. One, when you're dealing with cloud chambers, you're dealing oftentimes with like gases and liquids. Because of that, you're going to be oversensitive to things like pressure, temperature, humidity, all those sorts of things. Because of this, also, you can't just hand someone a cloud chamber and expect them to know how to use it if you want to use it educationally. And also, because of this, you don't necessarily want to build a giant cloud chamber. All these problems just exponentiate. So hopefully at this point, you see the avenue for this, where that's one thing, but it doesn't involve gases. It's running off of a wall outlet right now, right? And I just plugged it in and it started working. So this comes to the question of, how is this possible? Is there a way that we can accomplish the same things that the cloud chamber does and all these other gas-based detectors, but without all these caveats? So now I'll sort of talk about how we detect cosmic rays. And it's very simple. There's basically three components. Here is the basic core of our detectors. It's called a plastic scintillator. I'm also holding one in my hand. It's clear, feels like plastic. Doesn't seem special at first, but watch what happens when I put it up to a window. It turns this sort of bright blue color. Now, why is that? Well, it turns out that when a muon enters the scintillator, it excites the electrons to a higher energy state. And when those electrons de-excite, they emit a photon. How do we know? It's this blue light you see, blue light photons. And this is exactly what we want. When a muon enters, there's this clear signal that we have that it went through the scintillator. So now the question becomes, okay, we have this special material. That's not a gas or a liquid. It's a nice solid. How do we actually use this, right? How do we collect that light? So we have our scintillator. A muon goes in. This blue light gets emitted. Obviously, we're going to need a light sensor. And for us, that's going to be something called a silicon photomultiplier. You might hear referred to me as SIPM or SIPM. Basically, you can ask questions about this later. It has the ability to take single photons and amplify it through an avalanche effect to a measurable electrical signal. And has the added benefit of being really small. I'll show actual pictures of them later, but this is great if you want to build something as compact as this. You're not using a giant photomultiplier tube or something like that. So we have a way to detect that light. But now the question becomes, how can we make sure all the light gets to the sensor? And you might have noticed a nice groove there. And that's where the wavelength shifting optical fiber comes in. Its function is sort of in the name, but when the light hits it, it guides it towards the SIPM. So then we can make a signal. But it's also wavelength shifting. It's wavelength shifting towards the greener wavelengths, which you can tell because it's green. And why green? It's green because that's where our SIPM is most sensitive. So it has that sort of dual purpose of capturing that light and also being where it's most sensitive, right? So then there you go. Those are the three components that you need to understand to really grasp the very basics of how this works. And it's quite simple. Here's actual pictures of them. So those are the scintillator bars. These are the SIPMs. These are the fibers. And now the question now becomes, okay, I have all these materials laid out in front of me on a desk. How can I put them all together? And for that, there's a lot of preparatory work. For each one of these bars, the longest thing probably we had to do was polishing. It's a little bit choppy, but that's okay. So you actually have to polish each of the ends of the scintillator, and you have to actually polish the ends of the fibers. So there's a before and after polishing. And then this is me and Brent Clillan. We spent a long summer polishing a bunch of these. And we do that to prevent light loss, right? We want to make sure that when the muon enters the scintillator, we're capturing as much signal as we can because we don't want to lead to inefficiencies, right? So this is sort of the first preparatory step. That took quite a lot of time. The next thing you want to do, obviously, is looking at the electronics. How are you actually going to connect the SIPM to the bar? And for this, we have a nice enclosing 3D printed. I'm holding one here in my hand. And I like these images mostly because it gives you a sense of scale. Like, that's how big the SIPM is, right? I'm picking it up with tweezers. It can fit in this tiny little slot. And this way, and then there's a motherboard to actually get the readout. So at this point, you have all your components. You have a way to attach the SIPM. You know your materials are properly prepped by being polished. So now you can put it all together, right? So this is one unpacked module right there. The scintillator is a little bit hard to see because it's clear. But you see a fiber running down the center of it. Then again, in that guide bar is where the SIPM is. So this is great. You theoretically, at this point, have yourself a system that can detect muons. However, there's a slight thing that I'm leaving out here, is that if you put this exact scintillator in this state to an oscilloscope, you're going to get a crazy noisy mess, right? Because there's nothing preventing SIPM from detecting the lights in the ceiling versus like a muon, right? And this is where the packing procedure comes in. We don't just put them in this detector like that. So we first wrap it in this reflective material, aluminum foil basically. And that's so the light bounces around in the scintillator to eventually hit the fiber. And then we wrap it in this sort of black tape, and that's what prevents any like external light leakage from entering the scintillator. And then now you can proudly stand with your first module, and you have yourself a little muon detector, right? Now the only step to make this is to do that 17 more times, right? So you have yourself a single module. We went from understanding what cosmic rays are to theorizing how we detect them to building this little module. Before we get into how we can build more of these and how we can actually put them all together into a grid-like space, there's an important part that we're missing here, right? How do we know that it's working properly? How do we know that it's functioning at the correct rate? And for that, I'm going to highlight sort of 2 tests we do on a single module that helps us ensure that we know that it's actually working properly. So probably the first question you might ask when you have a module is, how many times does it miss a muon? How many times does it accidentally trigger? And for that, what you first have to do is stack them. So you first have to get 3, and then you're going to test the middle one. And why do we do this? Well, the short answer is that we do coincidence. Okay, what does that mean? So we stack the 3 like this, and you can imagine that there's 4 cases that can happen. So first of all, probably the best case scenario, a muon goes through and all 3 of the scintillators trigger. That's great. It's doing what it's doing properly. You can imagine a reverse side of this where a muon goes through. 2 of them happen. That's okay. A muon goes through, and the middle one doesn't trigger. You can imagine the upper case where only the middle one triggers. And in this case, these are both against the efficiency, right? And then the last sort of trivial case is that none of them go off, and that's fine, right? There's no accidental triggering happening. So all we do is that we stack them, stack 3 scintillators on top of each other, and we just sort them into these bins. And that's how you get your efficiency. And if you've made some plots before, this might be screaming at you that this begs to be a confusion matrix. Well, I got you. So here's the exact efficiency matrix for one module. And you can think of the total efficiency as just the sum of the diagonals, right? The sum of when they all go off or they all don't. So for this scintillator, we had an efficiency about 92%, which is pretty good. So this is great, right? We now know how often it accidentally triggers or how often it misses a muon to obviously some error, right? So we know that we've answered that question. But the next question you might ask is that our SIPM actually has to be charged to a set bias voltage. So how can we ensure that that bias voltage is the correct bias voltage, right? It does come with a little paper that says what it should operate at, but we need to test these things, right? In these larger experiments, you need to verify that all of your components are working as properly. And for that, we have this sort of SIPM characterization setup. This is somewhat more complicated, but I'll try to bring you all through it. We basically put an unwrapped scintillator in a black box to prevent any light leakage. And we put an LED pulsar, which is exactly what it sounds like. It blinks an LED. For us, it's at sort of nanosecond scale. And perhaps the best way I can explain to you is just go to the next slide, where we have our setup, the scintillator bar, LED on one side, and SIPM on the other. And the LED will blink. And every time the LED blinks, our SIPM will record a distinct number of photoelectrons, right? One time it blinks, it will observe 5 photoelectrons. Another time it blinks, we'll observe 2 photoelectrons. It's a sort of statistical process. So what we do to sort of characterize, make sure it's working properly, is that we look at what we would see on the oscilloscope. And as you can see, each time it blinks, we get a curve that kind of looks like that. And depending on how many photoelectrons you see, corresponds to the amplitude, right? If you get less, it's going to be a smaller curve. If you're going to get more, you're going to get a larger one. And to actually put a number on that, we just integrate it. So if you know V equals IR, you know that integrating voltage over time gets you the total charge deposited. So each time it blinks, we have this curve, we integrate it, and all we're doing then is going to put it into a nice little histogram, right? And I hope in your head you're kind of guessing what this might look like. Think about it as there's sort of a discrete number of photoelectrons observed every time. So what would this eventually look like? Well, here's an animation that shows sort of the long-term behavior of this. As we sort of keep on blinking LED, keep getting more into points, And again, every one of these points is an integration over the voltage over time graph. And you see that we get these distinct peaks, right? Theoretically, right? If everything's working as properly, this is something that we should see, where each of these peaks represents a different number of photoelectrons observed by the SIPM. Okay, so this is all just fancy animation, but do we actually see it? Well, let me show you those graphs. So, for instance, this is the charge graph histogram for when we charge the SIPM at 53.75 volts. And again, you can see these distinct peaks. And again, each time you look at these peaks, it's a distinct number of photoelectrons. And more than that, we can also test one more thing. As we increase this bias voltage, this number on the SIPM, that we get more charge per photoelectron. I'll let that sort of go for a second, which means that the actual distance between each one of these peaks should actually get bigger. Right? So what we did is that we took these charge histograms and we did it for multiple different bias voltages. So, for instance, here's just 4 of them. And we took the average distance between each one of those peaks, each one of those distinct photoelectron peaks, and we put it on a plot versus bias voltage, right? So each one of these dots corresponds to one of these histograms. And we expectedly see a nice linear relationship, which not only tells us that our SIPM is working correctly, which is great, but also tells us that we don't necessarily want to be charging it to 55.6 volts. As you see, this graph is a lot more noisy and choppy than its counterparts. So this is sort of a long process. I'm willing to answer more questions on it later, but this is how we ensure that the SIPM is working as we expect. So at this point, your fine might be itching to be like, okay, this is all just with one module. Let's actually now sort of put them all together and start to make something that looks a little bit more like this. And for that, I'll first start with the casing. This was designed by the great Sean, who's back there. You can kind of see the phrase we like to scientifically use is that it's Lego-like. So it has notches on the top, has antinodes, I guess, on the bottom. So then it can sort of slot into each other like this. So this way you can kind of imagine like we could make any kind of size detector we wanted. It's important to know that, so this is what we call a layer. And it's a layer because it has a pairing of sort of one layer that goes across one axis and one layer that goes across the other axis, right? So if one row goes across, let's say, the x-axis, the next layer will go across the y-axis. Why do we do that? Well, it's to get an increased positional information, right? We stack it sort of like Jenga, so that if we know that it goes through this scintillator and this scintillator, we know that it must go through like a little box above them too. So we do coincidence like that. So this is one layer, we'll call it. If looking at this diagram, you'll see that there's 3 layers. So three layers, 6 scintillators per layer. There's 18 individual muon detector modules, which go for all those other steps I described earlier, the polishing, all that sort of. And you might also glean from it that its resolution then, right, is going to be 3 by 3 by 3 pixels. Okay. And that's going to be important later. The next thing that's obvious about this, besides the actual casing, is that there's a blinking thing, right? So we actually had to build that. That took a lot of soldering as well. But the important thing to point out about this cube is that its resolution is 8 by 8 by 8. But our detector resolution is 3 by 3 by 3. So there's some mismatch there that we must address. So what's sort of the workflow there? So we have our detector. We have its 3 by 3 by 3 data. How do we go from that to the actual LED display? Well, the first thing we're going to do is that we're going to draw a line, and I'll get into more specifics later. So you can imagine points in 3D space. We're just going to draw a line. But then we're going to simulate that line, which corresponds to the muon track, in a higher resolution detector, specifically one that matches the LED cube, right? So we draw the line, then we simulate it in a corresponding 8x8x8 detector, in which case there's a 1-to-1 correspondence between that simulation and this LED cube. And to better illustrate that, I have another animation, I think. So yeah, it's a little bit hard to see, but you can see these are theoretical points in our 3x3x3 detector. We draw the line, and then we simulate it in an 8x8, where each one of these red boxes corresponds to which LED would light up. Right. So this is great. We now have a way to extrapolate our detector data to a visual display, right? And we need the visual display because that's what we're trying to do, an educational thing that does similar things to a cloud chamber, but without all those caveats. Okay, so now you might have noticed that I just casually said we simulated it in an 8x8x8 detector. That means we had to develop our own like sort of simulation script. It can handle a lot of rectangular geometry. I can answer more questions about it later. But you can see here, this is just simulating a muon in a 3x3x3 with some gap in between each pixel. This is simulating it in an 8x8x8. And this sort of script actually does the things I was talking about. It draws the line, and it draws the line over inputted detector geometry. For our cases, it's the 8x8x8, which we can then send to the LED cube. This also allows us to create synthetic data so that when we actually do data analysis of the real data, we're not going into it blind, right? We want to have this sort of simulation to get an idea of what the data should look like. Right? And I won't go too much into this, but how we actually draw the line is using singular biodecomposition, which is, for better phrasing later, it's just kind of like matrix manipulation to draw it. So at this point, we built one individual detector. We tested that. We now know it works. We built 17 more. We have ways to put it into a grid-like Jenga structure. And we have a way to translate the data to the LED cube. Okay, well, what's actually going to do that? What's the sort of brains of this detector? And for that, it's really simple. It's just sort of two boards. So on the left-hand side here, we have an FPGA, which will read basically the raw signals that we get from the detector and do coincidence. It does that sort of Jenga matching so that it outputs basically pixel data if you want it to. The Raspberry Pi will handle basically everything else. So it does the actual drawing of the line. It does the controlling of the LED cube. It also has some fun other things. You can get temperature, pressure information, and it controls like any other external display we have. And really the best part about this is that we just power it with a simple like wall outlet. In fact, we've taken it where we just power it off of like a phone battery bank, and it lasts for a few hours. So this is very portable, and quite simple design when you sort of break it all down. So I'll sort of now be like, okay, we built one module, we built the grid, we built the cube, we have the software to go from the detector to the cube, and we have the boards which will actually do it. Right? At this point, you're basically done. Right? You've built yourself a little muon detector which can display muons on this sort of 3D space, and it has all of those benefits, right? It's tabletop size. I just brought it over here from the lab, just carrying it. It's not going to be oversensitive to like temperature and pressure like a cloud chamber would be. Unlike a cloud chamber where you kind of have to like take a photo to like really record the data, this you can save as a bunch of CSV and be like, hey, you want some practice doing data analysis, student? We have this entire data set on this much simpler detector, which you can practice on, basically. So this has been up for about like 2 months, maybe. And we've already done some amazing fun outreach with it. So here is the detector on the 36th floor of the Cathedral of Learning. We also brought a full monitor and keyboard, which is why those two are laughing. We've also brought it to this Cooper, bring it to a poster fair, that sort. And this is us with a black tarp to take those fancy photos that you saw at the very start. So you know, if you have any press opportunities, we're welcome to bring this around. But it's not entirely done yet. There's some few other things I want to highlight before we move on. We're gonna add there's notches in here. We're gonna add actual panels so that if someone spills their coffee on it in like a public exhibit, it won't break. We're gonna have a web server hosted by the Pi, so like you can wirelessly just check on it without having to like plug it into like an external monitor. There's gonna be a smaller screen on the front, which we have. I mean, we have a student who I don't know if they're here today, but they're potentially working on an auditory component, right? Because that was an idea. Which is great, right? This is an educational display, so accessibility is important, right? So any way we can represent a muon is vital for you. There's some other fun uses we can do. Like again, you can be like, hey, you want to test different track fitting algorithms? You want some simple, like instead of working on like a giant cylindrical detector, it's like a 3x3 grid space. So you can detect, you can test a chi-squared fit, you can test an evolutionary fit, you can do all these things. And this bullet point holds a lot of weight. Feel free to ask me about it later. But we also have had fun making a graph neural network to do some things, and I won't explain this image too much. But this is basically the GNN identifying that there's 3 muons that happened in this event, and it drew 3 separate lines, okay? Which is something that like chi-square fit can't necessarily do without maybe some other logic to it. Okay, so at this point, I'll move on to the best part, which is that this is mini CoRTEx, meaning there's going to be a big CoRTEx, right? One of the things I emphasize about the cloud chamber and the issues with it is that you don't necessarily want to keep on scaling it, right? We have, by making this, had in mind what happens if we just add more bars? What happens if we make the bars bigger? So we're going to make the bigger ones, and it's currently happening. Those bars are going to be about like twice the length, so 32 versus 15. It's going to have a little bit of a different display, right? This cube is not going to look as impressive when it's next to a big detector. So this design will have LEDs on the side. I'll show another animation that displays that. And it'll just be overall better. Like you'll have charge information, timing information, more data that you can manipulate or you can give to a student and all that sort. And we are currently doing all those fun steps I talked about in the beginning when building a single module. The polishing, the cutting the bars, branding the jig, all that sorts. What am I doing here? Measuring, all that sort of fun stuff. So let me sort of show you what this might look like. So here's another simulation. So this yellow line represents a muon track. And every time it enters a bar, its end caps will basically light up. So instead of this tiny cube relative to that, we're going to have these LEDs on the side, basically. Okay, so at this point, hopefully, you can answer this question of how we're able to build this, right? We went from very basic principles, those 3 components, the scintillator, the SLPM, the fiber. We built one module. We then built a bunch of modules, figured out a way to put them all together, figured out the visualization, figured out all the necessary code that needs to go in between it, and you have yourself a little detector. But I would be somewhat remiss if I didn't mention probably the most important part about any of these experiments, and that's the amazing people that I had to work with. So give me a little bit of time to do this. As you can see, there's quite a lot of people. So I'll first like to thank, without this project, without this person, this project literally would not exist. And he's in the corner there, Raj. He's an amazing guy. And that's not hyperbole. He's amazing. If you get a chance to talk to him, talk to him. I like to thank my amazing advisors, Pranava and Tae, for continuous support. Again, I'll go through the current team. We have Sean and Cooper there who've been working for about a year. Then we have 2 great students. So I think only one is here today, Viviana and Al. I don't think is here, but they're going to be vital for the creation of actual big CoRTEx. So that's going to be great. I'd like to thank this guy. He's probably also prominent in these photos. This is Brent Cullen. He worked on this. So I've been on this project for, I think, 2 years. And he was here for the first year until apparently he had to go to grad school. So he's been really, a lot of this early work, he helped out a lot. So that's Brent. And then I would like to thank Sanielevici family. This was something really exciting, especially it's an outreach project, right? We have a physical prop. I was really excited to show all of you guys today. And then let's see, we'll also thank the honors dean for doing all of that, working cathedral, things, spaces like the makerspace down in Hillman, which I know Sean has a lot of experience with, making all this stuff. And you can also see so many other undergrads. When I was making this list, I think there was like 10 to 15 people who have at least polished the fiber, which is amazing. So, okay, that's it. I'll take questions. Thanks, everyone. There's a lot.
When you're testing three of them,
Yeah.
you have this matrix of four.
Yeah.
But you made an assumption that the outer two were perfect at doing that.
Sure.
And so what are the consequences? You never saw the outer ones fail or considered the possibility like they were some perfect.
So yeah, we only considered events when the top and the bottom triggered. Right. So it's not like we only triggered on when just one of them triggered as well. So we had to really like filter that. Now I do understand what you mean by like those efficiencies. We don't necessarily know either. So there is error with that, which I acknowledge. Perhaps there's a better answer to that.
But I guess like you rotated, right?
Yeah.
So I mean, the dot would become the middle one. So I mean,
Yeah. So it's a contained system that way.
Andrew.
So this was a really excellent talk. It's really exciting work. So I just want to say that first. I have a design question and then a really basic question. So the design question is, I'm just curious how you decided on the time scale to show your LED, right? Because
Sure. Yeah.
it's not unspeakable.
Yeah. Yeah. I mean, we did have a version. So one thing that we're assuming here is that the muons are going from the top to the bottom, right? So this is how this animation's working. There's no reason to do the animation other than it looks better, but there is a built-in delay here, which we're working on. Like this is going to run separately than like the data taken. So all that timing information will be as accurate as it can be.
So you don't know whether it's coming from top to bottom?
No, we don't have any timing information.
Oh, I see. And then my basic question is about the hot air balloon.
Yeah.
So if I understood you correctly, the source of the muons is when, a proton or something interacts with a particle in our atmosphere.
Yeah.
So it's not obvious to me that if you go higher up, you'll see more muons. If you go all the way up, you'll see none, right?
Sure. I think the best way to answer that in my mind is there is that point where I would assume there is that point that you're talking about where we see less muons, obviously, as you go out in space. I presume, wish I had the plot he actually had in his paper, but he didn't go that high up in this hot air balloon. Right? So he stayed in that range where that effect is prominent. But as you said, there's definitely that other effect where if you keep going up, there's less.
So it's a subtle thing.
Yeah.
I'm not wrong to have to think.
Yeah.
Okay, great. Thank you.
Yeah, this is really interesting talk. I guess one of the questions I have is, you were talking about like bringing this around to different places and showing like different science, maybe organizations and public organizations, all that. It's really cool. And so I'm wondering like, how scalable is this kind of project for like a kit or something? I can see you had a lot of individual steps, but now that you've gone through.
Yeah. So like for that, so like there's this other team that I'll point out. They're called Cosmic Watch, and they basically build the similar design as a single module, and those have been on like tour, and like I think at the time you can buy them like commercially and all that. So that is there. Now, obviously, if you want to build a big one, that's something you might have to contact us for and be like, hey, we want one that's shaped like this, one that's shaped like that. That will take a little bit more work.
Yeah, I would imagine it could be a pretty cool opportunity to like learn electronics. And
Oh, definitely.
Yeah.
So I'm wondering, when you take this around and use this as an outreach tool, have you thought about how you're going to convince people that this isn't just sitting there flashing on its own?
Yeah, I
When
mean,
you have the typical thing is when you have two panels of muon detectors and you put them in coincidence and you move them aside, they stop.
yeah, I mean, there's fun.
Firing. So something like that, or even to have a radioactive source.
Yeah, so that's the main. We've talked about radioactive source, but I think you would need quite a radioactive source to actually do that. Yeah, but that's a. I mean, some people here probably have seen me at poster fairs where this wasn't real data and it was simulated. So I understand. I understand.
Is it real data now?
It's real data now. 100%.
Are you sure? Raise your hand and swear.
Absolutely. Any book.
Is that real time?
There's a slight delay.
I mean, like that's not simulated, right?
No,
What is the delay? Can you say the
this one, I think we have a lot of scripts. I think this is only a tenth of a second delay.
Yeah, so
Oh, that's like nothing.
effectively it's real time. For this
For this purpose, it's
For the one at the top. Does it take more than 10 seconds to show the trick?
Yeah, and you never see two at the same time, right?
yeah.
So
no.
do you delay them to
Yes.
Now, Melanie, our former Sanielevici scholarship winner, is going to ask a question.
I have a couple questions. So, you're getting information about the flux of muons. Are you getting any, I guess you're not getting any information about their energy level?
Yeah. So this one, it's a very basic like electronical setup, and that I think the signals just go directly into like a discriminator. So we're not getting anything where like the actual pulse that it's producing. Now, if you were just to hook up one of these to an oscilloscope, like just a single module, then you can get that stuff. But this one doesn't accomplish that. That's something that we're looking at for the bigger one, getting more.
Yeah, because I'm thinking about like what could you do to sort of do different, I don't know, experiments with it, like,
Like, I think we have.
verifying the energy level would be one thing, maybe putting it in a balloon and trying to see what happens if you take it up to altitude or, I don't know, bringing magnets near it or something.
Yeah, I mean, we've I won't do it here, but there's a demo I can do where I put it on its side, and you can, different angles and all that sort of stuff. In fact, I think we have a detector here. I think Urosh built it, where you just put one of these on like a monitor stand and you can rotate it. And therefore, you can make a measurement of that polar angle, which we know to be like cosine squared or something like that. So yeah.
So, Andrew, I Googled the mean free path of a GeV proton through the atmosphere. And it's only about a meter. It's of order meter. Which means you can go pretty high.
Yeah, but there are two effects, right? One is production of muons, and the other is decay. So there'll be a point where muons would have decayed before you. So this
Right, my point was you don't get so high that you start reducing the flux. You see what I mean? Because they're produced almost immediately upon hitting the atmosphere. Anyone else have a question? Any other questions for our? Go for it, right here.
So if I'm pulling out my hand and some number of muons passing through in some amount of time, would that mean that they're all kind of getting hit simultaneously? And so how does it like choose which muon path to show?
Yeah, on the time scale of this, most of the time it's a single event. When there is multiple events, that's something where like an improvement in the software is going to be needed. So that's things like the GNN, when we identify multiple tracks at once, all that. But for this purpose, it's small enough where that's not a huge issue.
Have
you taken this on the road to schools, to like a grade school? Or?
Not yet, but if anyone has connections,
we can set you up with schools to go to.
So we can do that.
question here.
Yeah, kind of in the same vein, you kind of talked about like keeping on floor and like doing demonstrations and things like that, but is there any kind of idea or plan to have this be something that's more accessible for schools and like especially
Yeah. So like in theory, we can give someone a single a module and like hook it up to a counter, right? We can give them two of them and they can do coincidence, stuff like that. So in that sense, it's going to be like very much on a case by case basis. But it's important to know that we can do that, right? We can make a big display. We can make a smaller display. I see you.
I was gonna wait till you were done.
No, that's about it.
I have a three-part question. Okay. Related to these last two questions, though. This is it's kind of what I was thinking about. The LED grid itself, that must be super cheap in terms of materials.
Yeah.
Okay. So, wouldn't it be awesome if you made 1 million of those grids and you served the data out over the internet? I could just have that in my classroom, plugged into my computer, lighting up all the time. Like that would be an amazing outreach that could touch lots and lots and lots.
So that's what we're really pushing a server having.
Yeah.
But yeah, that's something we thought about, and that's really why we want to have like a web server up, so that someone online can go to our website
so awesome.
and hit download, and they have a data set.
That would be the coolest thing I've ever seen.
Download it from the cloud.
It's not a lot of data. You can serve it out real time, right?
Yeah. That's also
No, you can imagine like a high school science teacher. They just have it sitting there, and it's like lighting up.
It's like the new Newton's cradle.
Yeah, that's way better. That's got boring after about 2 minutes.
Tell us a little more about the simulation part.
Sure. Let me see.
Like when you say you went from 3 hits to 8 hits, it's not super obvious why you need to simulate it rather than just extrapolation, for example, or how simulation is done at all.
Sure. I mean, what is I should have put on the side. I mean, you could extrapolate a line, but then you have to make a lot of choices about where in the line corresponds to which place in the LED queue. So in that frame of reference, I can definitely argue that it's just easier to just simulate a more higher resolution grid space and check it that way instead of having to like check every point of a line and all that sort of stuff. So yeah.
Good question.
Maybe this is a comment to a bunch of questions that we've asked. Part of the process, the idea that we have for the project is that we'll make some of the information about how to make these detectors available in form of a set of guides and instructions on how to build them and all of that. So that part of how to help this make it larger rather than can build something similar. So we'll provide some code, we'll provide some instructions, so people should be able to do that themselves if they do need to have some equipment, some ideas, but they can of course they always reach us.
So we've also thought about how other institutions could do this also. And I had some preliminary talks with some friends who are high school teachers and colleagues who are at colleges. It seems very feasible for other colleagues at different universities to replicate what we do. But any level lower than that, there are significant hurdles. In fact, even if we cut and send all the pieces, my high school friend says we have nowhere to polish it. I said, what about the wood shell? Well, he's not allowed in the wood shell. There's significant hurdles. You need oscilloscopes that are costly to just test them. So it becomes at a point where we have to do all the polishing and the testing. Might as well start a company and just sell them packaged. I mean, if you wanted to do the science, there are some significant, it's possible, but there are significant hurdles. And if you wanted to do all the science, there's labor costs. That adds up quick. But at universities where they have engineers and where they have
equipment that they could just borrow, a $20,000 oscilloscope, no problem, then I think it's possible. They would still have to buy some scintillator material, but those costs are relatively cheap, on the order of thousands of dollars, and not, let's say, you don't have to accumulate tens of thousands of dollars, but it's possible. But I think you do a layered outreach thing where we can have them available. That could just be online and they can see it. That could be a way that younger students could engage. And then there could be like different packages available for different, if it's a smaller university, maybe they don't have a fancy something. But it's possible. But we want to start inwards out. And so we start with Pitt. Pittsburgh. Things like
Might have another minute or two for the last question. They're been pretty vibrant already. There we go. Look at that.
What inclined you to choose the blue LED?
Was I the one who made that decision?
I think this one with the cheapest.
I think
There was talk about like, is there a way we can control the color? That would be cool.
So
But he should have said he didn't have to do with
but the next page,
You have semiconductors.
we're going to measure the charge. So energy deposit. And maybe we can make it like a little bit redder or something.
Yeah.
If it's hot or if it's higher, so you can control it with colors and temperature. So you can see, it deposited most of its energy in the beginning, later, whatnot. That's also possible.
Yeah.
And with timing, the direction maybe the timing difference between the first hit and the last hit, maybe it's possible. Maybe it's possible. Probably not. Maybe it's not. Yeah. But we could, yeah. And someone mentioned the magnetic field. You need too large a magnetic field to bend the muons. But it doesn't prevent me from thinking about it. My neighbor is a EMC and just friends with big magnet. And it got me thinking that our detector itself has to be basically made all of plastic. So all the readout has to be downstream, not put the, it gets challenging. And I don't know if it's worth it, but.
About putting a layer of lead in the middle.
Very good, yeah. Yeah. Carolina says, well, instead of taking modules in the town, building, you can put shielding not just at the bottom, but maybe even at the top to start, and you'll see nothing. Side, you could do that, or partly, or maybe you could just take a module out, but that's probably risky touching it.
Actually, what would be cool is we put a light there in the middle and we see a shower from electrons. So track and shower of electron in the bottom.
Okay.
That would be
I'm
amazing.
talking too much, I'll
That's
stop.
what you're thinking, yeah.
But we're all very excited about it.
And back when we were kids, there was no such thing as a blue LED.
Yeah.
That's why
I was kidding. There was no such thing as a blue LED.
Wasn't no doubt for us.
That's right.
Anyway,
Yeah. So
now it's time to thank Kyle again. And of course, let's thank the Sanielevici family. Thanks, Kyle. That was awesome.
That was awesome. Excellent.
Really awesome.
Wow,
We got to talk about this idea of distributing.
I've seen it.
I would